Okay, so today we're going to be doing 5.5, which is remainder and factor theorem. So the remainder theorem states that when the polynomial f of x is divided by x minus a, the remainder equals f of a. Use synthetic or long division to divide the polynomial. The remainder is equal to p of a, where a is the zero being divided. Given that p of x is equal to x to the fifth minus 8x cubed minus x squared plus 2, what is p of 3? So here's what you do when they ask you to evaluate a value at x. We can use synthetic division to do that. So you're going to set up your synthetic division bar. And whatever you're evaluating p at is what you're going to put on the outside of the synthetic division bar. On the inside, you're going to put your coefficients. So you're going to notice that I put in placeholders for the x to the fourth and the x that are missing. Yes?
Why is it not negative when you put it in? Why is it not off?
Oh, good question. The only time it flips signs is when it's in this format right here. Otherwise, it's not going to flip signs. So, good question. Now we're just going to complete our synthetic division. And if you're still struggling with this, please review the stuff from yesterday. Combine, multiply, combine, multiply, and I get 20. So what that means is p of 3 is equal to 20. So the main thing you need to know here is, yeah, what's up?
So since we did synthetic division, do we have to do long division?
Yep, you remember yesterday when I talked about when you still have to do long division? When it's not in this format right here, you still are going to have to do long division. If it's like x squared that you're dividing by, if it's not x minus or plus a number, yeah. So what I was saying is, right here, what that means is when you do synthetic division with some number and you get some result, that's the same thing as plugging this number into the function, and this is what you would get. So I'm going to show you why that's the case. So if you then evaluate p of 3, if you were to plug 3 in for x, you also would get 20. So what you're going to notice is whether you do synthetic division to evaluate or you just plug numbers in, you get the same results. So that's the main idea to understand there. And is x minus 3 a factor? What do you guys think?
No.
No, because the remainder is not 0. Did you guys get a copy of the notes?
No.
Okay, 5.5. Yeah. Okay. The factor theorem states that k is a 0 of x if and only if x minus k is a factor of f of x. Use the factor theorem to find all real zeros given the polynomial in one factor. So we want to determine if x plus 3 is a factor of this polynomial. So to do that, we're going to do synthetic division and see if we get a remainder of 0. So what are we going to put on the outside here if what we're dividing by is x plus 3? Good. On the inside, we're going to put our coefficients. Don't forget your placeholders, if there are any, but I don't think there are here. All right. Anybody have any questions about this setup? Okay. I don't like the way that negative 1 looks. All right, so we start by bringing down the 4, multiplying, combining, multiplying, combining, multiplying, combining, multiplying, and combining. So, as you can see, that means that x plus 3 is a factor of this polynomial, right? So, how can we represent the quotient here? What is that going to be written as? 4x cubed minus 8x minus plus 2. And we know that if we multiply that by what we divided by, this whole thing would represent the polynomial. But our goal now is to see if we can use synthetic division to help aid us in factoring this thing fully. So as you can see, we've already somewhat factored it. So we started here, now we're here, but we want to factor this further. So what can I do to factor this polynomial portion here? I can do factor by grouping. So we're going to do factor by grouping. So over here, I can take out a 4x squared, which leaves me with x minus 2. And then over here, I can take out a negative 1, which leaves us with negative 1 times x minus 2. And then if you remember, with factor by grouping, the common factor gets grouped together, what's on the outside gets grouped together. And we end up with something like this. Now, is this fully factored, or is there more we can do here? There's more. We can do difference of squares, because this right here is the difference of two squares, right? So this can then additionally be factored one more time into 2x plus 1 and 2x minus 1. So it's just a bunch of factoring, but the main idea I want you to take away from this is that doing long division can help you aid your factoring. If you do the division once, it helps you get down to a part where we're able to factor from there, okay? So any questions about how we got the factored form of this polynomial using synthetic division and our factoring skills? That's difference of squares. Any other questions? Okay. So now we're going to kind of work backwards. So sometimes they're going to give us the roots of a polynomial, and we have to work backwards to find the actual polynomial itself. So basically, anytime that you want to work backwards, here's what you do. We know, for example, you don't have to write this. If I have a factor of x plus 2, that would yield me the root what? X equals negative 2. The sign's always going to change, right? So here's how you set up. You go from roots to factors every single time. You always do x minus whatever the root is. In this case, one of them is negative 1. Okay, that's step 1. So we dealt with the negative 1. Now we're also going to do x minus negative 1 plus 4i. And then we have one more thing to worry about here. What type of root is this? Imaginary. We know imaginary roots have to come in pairs because there's always a plus and a minus. So we additionally know that our polynomial must also have a factor, negative 1 minus 4i. So we have to make sure we include that factor that's not just explicitly stated to us, that we go and find it, right, using our knowledge of imaginary numbers and conjugates. So we get to this point. Now what I want you to then do is basically multiply out that negative 1. So you're going to get x plus 1 times x plus 1 minus 4i times x plus 1 plus 4i. So you get to this point right here. Now we're going to have to multiply all of this together, but what we have right here effectively is two trinomials. You guys see that? Two trinomials. What's going to be the easiest way to multiply together two trinomials? Box method. So we're going to use our box method. So I'm going to set up a box, and I'm going to have 9 boxes in that. So that's going to be x plus 1 negative 4i, x plus 1 positive 4i. And then from here, we're just going to multiply the corners. So we got x squared, x, negative 4ix, x, 1, negative 4i, 4ix, 4i, and lastly we get negative 16i squared. Now what do we know that negative 16i squared is equal to?
16.
regular 16 because I squared is equal to -1. So now we can identify our like terms. Aren't these like terms right here?
Yeah.
And also these, right? And these. And also these. So we can go ahead and write out what we have left. So don't forget we still have that x plus 1 on the outside that we haven't dealt with yet, times x squared plus 2x. These are going to cancel. These are also going to cancel each other out. And then last thing I have to do is add the 1 and the 16, right? Which is 17. So now we're closer to the final answer, but we're not there yet because now we have to multiply a binomial and a trinomial. So we're going to do the box method one more time. So these problems can be a little tedious. You're not going to have to do a ton of them, but it is important that you understand the process at least once. So we're going to set up our box again. And we're going to multiply. We got x plus 1, x squared plus 2x plus 17. And then we're going to multiply in the boxes. And then the last thing we need to do is just simplify and combine like terms. So I have like terms right here. So I got x cubed plus 3x squared plus 19x plus 17. So this right here is the polynomial. So this polynomial right here has these zeros, okay? That's what we just found, the polynomial that has those zeros. So does anyone have any questions about that process? Yes? Why did I cross out the what? These ones? This right here? Oh, it was just me showing you that I already like took care of dealing with that one by writing it in the form of a polynomial. Yeah, it wasn't like actually crossing it out. It was just like showing that I had already used it. Anything else? Okay. So the last one we're going to do is find a cubic polynomial in standard form with the zeros -2, 2, and 3. So we set them up in our binomials, x minus -2, x minus 2, and x minus 3. So what's going to happen with the first one? It's going to become, it's going to become a positive. So we're going to have to multiply these three trinomials together. So I'm going to start by multiplying the first two together first. What do you notice these polynomials are? They're a special type of polynomial. They're difference of squares. So I only need to multiply the first and the last. And if you're wondering why, you can try it out. You're going to notice the middle terms will cancel because they're difference of perfect squares. And then I get here, and how can I finish undoing this factoring? Just doing FOIL, right? First times first, outer times outer, inner times inner, and last times last. And since there are no like terms we can deal with here, we can write this as our final answer. Now if you wanted to check your work, you could factor this by grouping and make sure you get these zeros. If you want, you can try it out. Alright, I'm going to hand out your homework.